Good morning. So yesterday, I shared with you some of that observation of plasma-assisted combustion in different environments. I have supersonics and internal combustion engines and ignition. And also, I convinced you that plasma is doing much better in terms of ignition and then flame speed. And now we also showed you some data in terms of experiment showing that the plasma can initially accelerate flame ignition in a flame kernel growth. But it does not really help to enhance that flame speed. So that question really is intriguing me to understand. And can we do an experiment and fundamentally to understand that when and where that the plasma can enhance that combustion? So I guess everyone learned this curve. This is that the typical flame temperature as a function of time. So this is one of the most important curve when I learned with a graduate student. And my advisor at that time told me that this is the foundation of combustion. And because it's saying when ignition can happen and when flame will die. And so that is the limit conditions. So anyone can change this curve. We are shaking the foundation of combustion. So I keep this thing in mind and through all my research careers. And can you shake the foundation of a research phenomena or law? And then you have a dramatic advanced understanding and that they have impact in technology. So let me show you that if you're looking at, if you believe that the plasma is very good in ignition, this is that ignition extinction. So if we can accelerate ignition from this point and back the way to here, that the ignition time is even shorter the time for of extinction. So if we can do that, then the whole curve becomes not S curve anymore. It's more like a monotonic straight curve. So here, then you don't have a extinction anymore, and anything you get in there will continuously burn, depending on how much combustion completeness will be. So that triggered me to experiment around that around 10 years ago. So here is the experiment you can see that is methane, and in a countable flame. So here I have a methane, and here maybe you have oxygen with a 34 or 62% of oxygen in the stream. So you can see if you have oxygen is very low concentration. And when you increase the fuel concentration at high fuel concentration, of course, you cause ignition, and then you go into the flames. And you reduce the fuel concentration, you die, the flame. So it's a typical S curve like this, and in combustion book. But now you try to say, I've tried to enhance that ignition by increasing the oxygen concentration, and so that I can create more atomic oxygen to accelerate ignition. So you do that, you can see, indeed, you can see the experimental lab, you can see that this is from that is the reaction to flames, continuously transition from a mixture and to a flame. There's no extinction at all. So I thought this is very intriguing and very exciting in terms of combustion. So that means that the non-thermal plasma, they can dramatically enhance ignition chemistry so that they help the flame stabilization through ignition-assisted flame stabilization, even though they may not impact much about the extinction limit. I'll talk about it later. So this is something that really prompted me to understand and how that happens. So everybody knows that a low temperature flames, for example, dimethyl ether, and they have a low temperature chemistry. So at that time, around 2014, I was asking my students, so if you can enhance the low temperature reactivity or ignition, you should be able to see a low temperature of flames in the laboratory. So we did this dimethyl ether, replaced that the methane by dimethyl ether, and then we watched that the formaldehyde formation as a function of how much fuel you put it in. And you can see at very little fuel, of course, that the reactivity is very low, and the heat release rate is very low. And you can see a lot of formaldehyde is formed even at very low fuel concentration. So at this regime, you cannot have any kind of flame to be formed because that is outside of the extinction limits. But you do see a lot of formaldehyde formed. And at a certain point, suddenly the formaldehyde decreased, and then the flame transitioned to a hot ignition, and a diffusion flame is formed. So this is a clear indication that plasma can do a dramatically enhanced low-temperature combustion. So that is something it triggered me to ask the question, at what condition plasma can enhance low-temperature combustion, at what condition they cannot. So you can see that if you further, for example, if you increase that I guess that this is the oxygen concentration, you can see the low-temperature ignition transition to high-temperature ignition smoothly without S-curve. So this is, I think, that is significant in terms of understanding about the fundamental combustion dynamics, that ignition to flame transition can be all right, so it's better? So ignition to flame transition can be through ignition extinction or directly transition to it. And I will show you how that will change that the cool flame later and remind us. So this is that battery around 2013, 2014, 10 years ago, I started thinking about this problem. And then, so if you're looking at combustion chemistry, everybody taking Bill Green's talk, at high temperature, if you have a fuel that will be attacked by the radicals, OH, that fuel will become a fuel radical, and the radical becomes the aldehyde, and then forming like a vinyl radical. And this vinyl radical at high temperature, they are not stable, and they either become HCl, and by reacting with a radical, OH, H, or something. And this H and HCl, they give you H radical, reaction with O2. H plus O2 generate a chain branching, and more radicals generate and form the oxide. So this is very clear. This thing only happens if the temperature is above probably 1100 Kelvin, around that. But if you have a lower intermediate temperature, this fuel radical, they can't become to dissociate into a vinyl radical. They don't have the energy to dissociate. Then what they do that they basically they work with oxygen and they attract an H radical, form HO2. This HO2 reaction, they form a hydrogen peroxide, and that at around 950 Kelvin, they decompose and become two OH radicals. You can see this is the high temperature chain branching reaction. This is the intermediate temperature chain branching reaction. They give you two radicals. So then you go to, if the temperature is very low, everybody knows that this few radicals, and they even cannot attract H radicals directly by oxygen. This oxygen just attached to the few radicals, and then isomerization of the molecular structure, they move that H radicals from the alkyl radical and to this side form a hydroperoxy radical. And they continue acting oxygen. This is the low temperature chemistry. And eventually they decompose, they give you multiple oxygen. So these are the three temperature-dependent reaction pathways. And they are all chain branching, but it happens at a different temperature. So I asked myself at that time, I look at this diagram, I draw, I said, look, if plasma is indeed really can promote combustion, where that it can promote most? So answer that question, I say, now I have a plasma. I can generate everything the D, O, and radicals and the oxygen molecule vibrational. So that can react with a few radicals, and that goes this way or goes that way, this way. Which one is faster? So that we have to understand that the at least understanding about the plasma chemistry. You can see that this is that the electron impact reaction generated O atoms, electronically excited. And how is this reaction rate? This reaction rate, suppose, is that one of the dominant high temperature chain branching reaction, but it's very slow until 1100 Kelvin. But in plasma, And this guy can be 100 times faster, and because that electronically excite molecules. And also you have one O singular D reactions that electronically excited. They can react with fuel here. They can directly absorb OH or insert into the fuel molecules. And then you can see that the nitrogen, electronically excited nitrogen, they can here vibrationally, they react with dissociated oxygen as well. You have a nitrogen vibration, you have vibration with this. All these things are least understood in traditional combustion chemistry. We don't have a good rate constant for these reactions. So when you see this, you start to see a big opportunity in doing combustion research. In combustion, we are talking about a reaction rate about 30%, 50%, 20%. Here, you're talking about a factor of 2 or even an order of magnitude. So, and keep in mind, we have 3 chain branching reactions, respectively at a lower, intermediate, and high temperature. And plasma can accelerate most, particularly in low temperature, because low temperature reaction is so slow, and intermediate temperature is also slow. The high temperature combustion, because it itself is very fast. Once it's on, it is on, unless you are near the extinction limit. So when I look at this, and I basically talked to my graduate student, Wan-Ting Song, and also that Sang-Hee Wang. I said, with this, with plasma, you probably can see a cool flame and a warm flame and a hot flame with plasma in the laboratory. So that just looking at. If you're looking at ignition delay time for enhancement, for example, you have a temperature and you have a time. And this is at the low temperature ignition and after a while, and this is high temperature ignition. So the high temperature ignition typically occur at high temperature by H plus O2 reactions. So if you're looking at that, so plasma can generate radicals. Particularly low temperature plasma can generate radicals. But the radical concentration is only at 100 or less than 100 ppm level, very low. So at high temperature, and you got this H plus O2 reaction. This reaction, once it's on, is very fast. And in the flame, they give you hundreds of ppm radicals. So therefore, plasma in this regime, instead of giving you the critical radicals, is just providing you that heat. You can accelerate this reaction by itself. See what I'm saying? So this is like a rich people, you give them a few dollars, $100. It does not matter much, right? But at the intermediate temperature, if you seek that intermediate flame chemistry, here you have a formaldehyde formed by low temperature chemistry. With a radical, you form HCl. HCl and you form HO2. HO2 goes to H2O2, and this dissociates at 950 Kelvin. This process is relatively slow. So therefore, the radicals generated by a plasma, they can dramatically enhance this one. And then if we go to even lower temperature, this R2 chemistry and the QOH chemistry, they are even slower. So therefore, plasma has a dramatic opportunity to enhance low temperature ignition and combustion and even flame speed. And this one, that the intermediate temperature. So to understand this diagram and the time scales, research sometimes is always about time scales and length scales. You understand this time scales, and then you will start to work on plasma-assisted low-temperature combustion that I have been focused on a long time and in the last 10 years. So let's show you something that the ignition, right? Ignition delay time is a function of temperature. This is enhancement. If you plot the ignition delay time, this is that red curve and black solid curve. They are ignition delay time with and without maybe 100 ppm of OH. That is plasma can deliver. So if you plot that the low temperature ignition on the curve, so here's the low temperature ignition, here's the low temperature ignition with 100 ppm of OH. What you can see that ignition delay time at high temperature is not much reduced by plasma generated radicals. But on the low temperature side here, and you can dramatically reduce the ignition delay time. So that means plasma enhances low temperature chemistry much more effectively than high temperature. And more importantly, in this region, around about 950 to 1,000, in this region, you can see the low temperature chemistry ignition is dramatically reduced by one order of magnitude. So this is that opportunity you want to use, and using plasma, whatever is doing combustion or low temperature chemical reforming, because they are hungry for radicals and what you can do to help the reaction. So recall that high temperature, you got the hydrogen with oxygen to generate two radicals. And the intermediate temperature, this process gives you two radicals. And the low temperature, and this process. And they have a different kind of oxygen. This depends on one oxygen. This depends on one oxygen. This one depends on two oxygen. So therefore, low temperature is much more enhanced by plasma-generated radicals, but more dependent on oxygen concentration. So higher pressure, higher oxygen concentration will dramatically improve your low temperature reactivity than that of the high temperature chemistry. So this is a very simple analysis without digging into any reaction rate. So I show you this is that Rich Yetter and research. He built a flow reactor. He put a electrode and this dielectric barrier discharge. And what he found that this is a comparison that the fuel oxidation, if you without, for example, a plasma discharge, you can see that the oxidation only happened around 1,000 Kelvin. This is typical because this hydrocarbons are pretty stable and at that temperature. But with plasma discharge, you can see that even at 500 Kelvin, and then you start to see all kind of oxidation happening depending on experimental condition. So this is the work and also the 2015, and I already confirmed plasma can dramatically enhance low temperature oxidation. So this is something I try to give you a summary. So this is around 2013 at that time, and I said, okay, so look, if plasma is wonderful, then it should be able to stay a cool flame. I'll tell you a story that at that time, probably 2013, my postdoc right now, professor at South Carolina, Yiguang, I showed him that diagram. I said, you should be able to use in plasma to see a cool flame in laboratory. And he doesn't believe me. He just said, we were in the lab, and I talked to him. Every time asking, he just ignored my question. So one day, after probably 6 months, I asked him, I said, Sang-Hee, I really need an answer from you. You just tell me yes or no, right? By 3 o'clock, just let me know yes or no. If yes, I'm happy. If not, I give up. And at 2 o'clock, and he came to my office. He said, Professor Ju, come to the lab. We see something very interesting. That is the cool flame we observed in the laboratory. It's the same condition, and they put a plasma-generated ozone, and they can see that the flame is stabilizing here about 6 months. This is the first time people be able to establish a visible cool flame in the laboratory. Before, it was more like flow reactor or just unsteady transition. So with that, and then you can see that with the plasma discharge, you can see a cool flame and stabilizing in situ plasma discharge. So all this experiment, I think that they show that how much that the plasma enhance the low temperature chemistry, and they can allow you to do something that you could not do it before, right? So that is really very encouraging. So after that, I showed you yesterday before, and we locked a lot of, we see a lot of experimentally see flames, cool flames and warm flames, and also due to these 3 chemistries. Question?
In the previous system, you showed what kind of plasma?
Well, this is very simple in the beginning. This is the nanosecond plasma. This is that plasma-generated ozone. So this is have electrode here. You have a nozzle, is an electrode. You generate the in situ discharge. Right. Yeah, pulse. And you run in probably about kilohertz, so you can see. So this really flourished my research. And then for premix flame, for diffusion flame, we can see a premix flame. We have cool flame. You have a double flame. We have not been able to see a premix warm flame yet because that they quickly transition to a hot flame. So we hope to see, we're trying to do experiment to see, so that if we can see a warm flame and a premix flame, so you can really dramatically. So here is a diagram, try to draw your attention. This is a diffusion flame. This is a premix flame. So premix flame, you can see the flame temperature and this equivalence ratio. And typically what you see is high temperature flames near stoichiometric. If we go to field rich, and you can see that the flame from hot flame and continuously reduce to cool flame without extinction, right? And then if you have a lean flames, you can see the hot flame temperature drop around probably 1200 Kelvin, they just extinguish. And then they drop to another branch is cool flames. And if you increase the equivalence ratio, the cool flames still stabilize the ignition. Why there is no ignition extinction transition here, and why there is ignition transition here? So this is this is unsymmetric, right? Why that the S curve is unsymmetric on the lean side? So one of the key reasons is that at the lean side, you have a lot of O2. So HO2 reactions that they give you heat release. Once you have heat release, they trigger all the ignition very quickly, jump to the hot flame. So that is how you learn chemistry and how do you explain the phenomena. And on the rich side, on the diffusion flame, you can see that near the flammability limit, you have a hot flame, and the hot flame die, they form the cool flame. If you reduce the stern rate, you can see the warm flame. The warm flame is very hard to observe because the stern rate is very low, unless you go to International Space Station. So there are people try to plan in the experiment, try to observe this warm flame, and in the International Space Station. And then I worked with Niels Hansen to see how that the ozone was generated by plasma can react with a ethylene, which was experiment done by Eric. So this kind of ozone, when you see a double bond, the ozone try to attach to the double bond to form a ring structure. This is that the ozonite. They break the double bond and form the ring structure. This ozonite, they decompose to a creaky intermediate, and this is very reactive. It can become HCO and OH, so they can generate this a bunch of radicals and a product and very quickly. So that can dramatically enabling that the reaction at room temperature. So that you can see this is that the temperature, this is that the signal of reaction between ozone with a methyl hexanoate. So typically that low temperature chemistry, and if you look at Bill Green's talk, it is happening around above a 300 something, and this is the low temperature chemistry regime. And you form this intermediate species. And then, but with a ozone reaction, you can see that they start from 450, and you see a lot of reactivity even at a very low temperature. And this 450 is because that the ozone decomposes at 450. They trigger this reaction and generate O atoms, accelerate extreme low temperature chemistry. So this is a very interesting result. And to see how that the plasma generates a long lifetime species like ozone can accelerate low temperature chemistry at extreme low temperature. So the next thing that is try to see that what happens if plasma can generate NO. The plasma can generate NO. For example, you can say N-heptane. This is that is the mole fraction of fuel and a function of temperature. So you can see that with plasma generated NO or NO addition to N-heptane, you see the low temperature chemistry slow down. The low temperature chemistry is slowed down by NO, but that intermediate temperature chemistry is accelerated. This is because you have RO2 chemistry that for low temperature branching that attacked by NO, they form this RO and NO2. They lost that chain branching pathway. That's why they delay the low temperature ignition. But at the high temperature, this a catalytic reaction of NO catalytic reaction, a NO reaction with HO2, they form OH radicals. They accelerate oxidation at high temperature. So with today, you have this ammonia combustion. They form a lot of NO with plasma or without plasma. That can tremendously couple with low temperature chemistry and intermediate temperature. Maybe allow you to observe something you don't see before and in hydrocarbon flames. So we can see that in the laboratory, we can see that this is the temperature of the counter flame with strain rate. We can see that without NO, the flame is like a hot flame, warm flame, like cool flames. And with NO, you can see that the cool flames barely receded and inhibited here, but the warm flame extended to a high strain rate. So that means clearly indicating that the NO coupling with low temperature chemistry that can enhance the intermediate temperature and enhance the high temperature combustion. So this is something I think people need to understand, that how, particularly in ammonia blended fuel, how this will happen and in terms of combustion and stability. So I talked a little bit about the flame. So the next thing I want to talk is something that adiabatic flame propagation. I think you already took the class about theory. I don't want to talk a little bit more. So when I was a PhD student, only thing I did is doing analytical solutions. I have a governing equation, I have a boundary, I have a one-step reactions, and find the solution. So I don't have to talk to details about this. Let me fly through. You just do an integration to find that adiabatic flame temperature. You do integration across the reaction diffusion flame zone. You find that the conservation between temperature and species. And now that you do normalization of all this temperature, species, and using this activation energy beta, you assume the beta is large. So that means the flame is very thin. So the thin limit, and you do a reaction, widened reactions. You integrate this equation across the flame zone, and then you integrate this. You found that the gradient, after you integrate this equation, you find the gradient of the fuel in front of the flame, the negative in front of the flame, is relevant to your reaction rate. So this is at the jump conditions of the conservation. By plugging this, then you integrate that the flames from the initial far field, initial conditions, all the way to the flame front. And this is the conservation equation. How much fuel is burned relevant to your gradient. You plug in this one into here, and you get this solution about flame speed. The flame speed is a function of Lewis number, is a function of activation energy, and etc. So this allows you to see and how that the plasma can enhance combustion through activation energy or through the reaction rate and Lewis number. So it's nothing here. So now that with the plasma, and you really have that you have a term which is heat, normally the heat loss or is heat gain. By doing the same metrics, what you can do is, I try to fly through this, and then you can read it. You can find an equation, normalized flame speed, and with a log of normalized flame speed square equal to 2H. H either is heat losses or is heat addition by plasma. So you can see that how plasma heat release is going to affect the flame speed in this regime. So this is at the normalized flame speed. This is at heat losses. The flame extinguished at 60% of flame speed. If the flame speed drops by 60%, and the flame will die. And this is that defined as a flammable limit. And how does plasma change flammable limit? Because they can change that the activation energy, they can change that the heat release in the flames. Now, so the next thing I really want to show you, and many of you may know, you may not know, that flame speed in a stretched flame and the flammable limits. So in combustion society, and when I was a graduate student, there was a big argument. People try to measure flammability limit using flat flame, using counterflow flame, using spherical bomb. And often they find that the flammability limit in 3 different geometries, they are different. And I was really puzzled that why that the flame speed, a flammability limit, or flame speed measured near the flammability limit in a flat flame, spherical flame, or counterflow flame, they are different. And what is the flammability limit from the experimental data? So that was puzzling, I think, that for combustion community for many, many years. People did not have an answer why they are different. So I want to analyze this. So we write down a governing equation. This is at the countable flame, and you have stagnation, you have a flame. This is strain rate, everybody in this room know. You write down governing equation that a convection, diffusion, combustion, and radiation, heat losses. And you write down the governing equation, whatever you want to do, you can follow the notes. I don't want to go to too much detail. And this is at the solution, normalized equation. And then you do a perturbation. The flame is perturbed from the equilibrium conditions to a small perturbation at large activation energy. And you can integrate the outside solution from that the flames. And you can create a jump condition by integrating the flame across the reaction diffusion flame. And then you can integrate that the mass and energy conservation across the flame. And you put them together and solve a perturbed equation. This is only a perturbed equation because that unperturbed, they are already solved. So then you can find a solution. Here it's very interesting. The solution tells you that the strain rate as a function of flame location, this is G is a function about anyway, is a mathematics. And this is the PF. The PF is that enthalpy change due to L is the loose number minus 1. This is the flame location. The G is this function. H is heat addition in front of the flame. H minus is a heat addition of the flame. If you look at this mathematics, it's very messy. But if you take a limit that if the flame stay far away from the stagnation, what does it mean? It is unstretched planar flame, right? That recover, that's the solution we just give it before. But my interest is that what is the relationship between the planar flame and that stretched flame? From this solution, I can analyze it because they give me a free unstretched flame and also give me a stretched flame. I'll show you something you may not understand. So here this is the flame location as a function of strain rate. That this is the fuel concentration, the loose number is less than 1 at 0.29. This is the concentration, the flame, the mixture is below the planar flame flammable limit, okay? If you set up a planar flame, free propagating flame, at this free concentration, you don't have a flame. But in a stretched environment, you have a flame stabilized here. And when you increase the strain rate, there's no time for reaction to complete. You have a stretch extinction. If you reduce that strain rate, that the radiation, the flame becomes thick, the radiation will kill it. So they will have a radiation extinction limit. So you can see a flame can only exist in a certain strain rate in a counterflow. So this is why that many people in experiment, when they do measure flames, they can see a flame in a counterflow flame, but they never then can see a flame in a flat flame. Because in a flat flame, this one is already below the flammable limit. See what I'm saying? And this flame has two extinction limits, stretch and radiation. So now you slightly increase the flammable limit, very close to the flammable limit, 0.29. So you can see that this flame branch becomes this, and they shift it to higher strain rate. But in the far field, there is another flame branch showing up, and they only exist at a very, very small strain rate, just like a flat flame. And then they extinguish at a higher strain rate. So when you further increase the strain rate, this weakly stretch the flame, they move to higher strain rate, eventually they inactivate, and then they merge together. This is what that flame typically people knew. So this from here to here to here, that relationship determines what is that flammable limit between stretched flame and the counterflow flame. I think that this is something I try to show you. Maybe the combustion book doesn't have it. So you can see this is the strain rate of, this is that equivalence ratio. For propane, if you're using counterflow flame to measure it, you measure the extinction limit. Hey, at this fuel concentration, the flame will be extinguished. If you extrapolate it to 0 strain rate, and you got this is a 0.5 or something. This is flammable limit, exactly the same as the spherical flame measured by Peroni in microgravity. So for propane, when the Lewis number is greater than 1, then the counterflow flame measured extinction limit, flammable limit, is the same as vertical flame. But for methane, remember, this is the flammable limit. But below the flammable limit, you still have a region that the flame can survive. And at high strain rate, you have stretch extinction. At low strain rate, you have a radiation extinction. And here, at a certain point, no flame can exist. You cannot extrapolate this one to this way. They don't extrapolate. So this was the pulse. This was the confusion in combustion community to what flammable extinction limit can be extrapolated and what cannot. Theory really can help you. Whatever, how many experiments you do, you don't understand this until you have a theory. And computation, you cannot do it either, because when the strain rate is close to 0, how much bigger domain you can compute? You just cannot. So if I plot this flame, and this is that experimental data, and this is what's happening in terms of diagram of flames. Combustion people should understand this. This is the temperature of flames, and this is the strain rate. So when have a very high, when strain rate is 0, this is the flat flame, that is the flammability limit, okay? And when you increase the fuel, the fuel concentration, that you can see let's say fuel concentration is equivalence ratio is 0.46. You have a far field weakly flame, another flame. This is a weakly stretched far field flame. And at the same time, below this flammable limit, you have a small island that is the stretched flames. And they have radiation extinction, stretch extinction. If you increase strain rate, they grow and they grow, and they grow and they grow. And then at a certain point, they merge. The far field flames, weakly stretched flame, and then stretched flame, they merge, they form a single eye line. And this is that extinction limit of the weakly stretched flame. And this is the extinction limit of the stretched flame. This is the radiation extinction limit. Only the weakly stretched flame extinction limit for Lewis number, even the Lewis number is 1.4, that can extrapolate flame rate. This stretched flame, you measure it, they cannot be extrapolated into flammable limit of flat flame. I draw you more clearly diagram what it is. So this is equivalence ratio. This is at the flame temperature, and this is the strain rate. Okay, so this is at the stretched flames. You can see here. The projected is a stretch extinction limit, and then here you have a radiation extinction limit, and you have stretched ignition. This is the far field flame. Okay, one weakly stretched flame. This extinction limit is projected here. Only that weakly stretched flames, they can extrapolate to the flammable limit. And then the stretched counter flame extinction limit, they cannot extrapolate into the fundamentals. So I think this is so wonderful to understand, and how theory is so powerful. They can understand something that computationally is impossible, and an experimentally is also impossible. So I think that in combustion, chemistry is very important, but theory and physics is also important. So I try to show you experimental measured how that for a Lewis number less than a critical Lewis number. The critical Lewis number is typically greater than 1. And it depends on the radiation intensity. So you can see this kind of a curve, and a stretch extinction, radiation extinction, they cannot be extrapolated, but only the weakly stretched flame. And for hydrogen, is something like this as well. It's stretch extinction limit, it's radiation extinction limit, and only this weakly stretched flame they can extrapolate. But for propane, no problem, and no problem. So this is that when you try to do near limit flames, you need to understand that the coupling between that the chemistry and the strain rate, and also that the Lewis number. So now we try to understand can plasma enhance flame speed, right? So we understand that the plasma can enhance ignition to make ignition-assisted flames. So we did this old days when I came to Princeton, assistant professor, and I did this experiment. I said we have a counterflow flame. We're using gliding arc to activate the fuel and air and see how that the extinction limit can be enhanced by the plasma. So we did that strain rate of extinction, as a function of how much methane and in the fuel stream or hydrogen. You can see by increase that the power of plasma, and you can see that the extinction limit continually to increase. So this was very happy by the program manager. But to me, then I try to understand that they compare, if I'm using this same power, just heat the air and compare with a gliding arc, I found that we measure the OH concentration and peak flame temperature. They give me the same result. You're either using plasma to heat the air or using plasma to activate the oxygen in the airstream. They do the same thing. The chemical kinetics of plasma enhanced does not affect much about high temperature flames. Why? As I said before, because the high temperature flame, they produce radicals so fast by itself. The only thing for the plasma to do is adding more heat. And that was very discouraging. So that triggered me that I give up in terms of plasma enhanced flame speed measurement. Instead, I try to understand how plasma chemistry affects ignition, affects the kinetics. So I started looking at the diagram, and plasma can generate NOx, can generate ozone, O singlet, OH, and so on. And how this species is going to affect a combustion and how the reaction rate will be. So that really intrigued me a lot. So I tried to work on this and to understand these reactions. The first thing I did is see how ozone enhances the flames. So you can see that by adding ozone into the mixture, you can see that the flame speed increased by up to 10%. So ozone, that is, you can put a large high amount of ozone into the flames that can give you O radicals at a high temperature that not only can increase that heat release, but also increase that some reaction pathway. But in the end, that the flame speed enhancement is about single digit. It's not a factor of 2 or not an order of magnitude, just like ignition, right? So therefore, you have to understand what is the limit about the plasma-assisted combustion, what it can do, what it cannot do, what it's good at, what it's not good at. So, and also another thing I try to do that using that O2 singlet. So this is one of the most important species and in plasma generation. So if you look at the oxygen diagram, so this is the ground state, and this is that excited state of most electronic excited state of oxygen, that is O singular delta. So that one is much faster than this reaction rate by order of magnitude in terms of, if you zoom it up, it's like this. So they have a ground state to a singular delta and a singular sigma. And that is the only require less than 1 EV, 1.5 EV, you can excite it. So what if I excited this molecule into singlet? How does it change my flame speed? So I hope that because this reaction rate is 100 times faster than this at room temperature. I had a lot of hope and I tried to see a magic to happen. But then I did this experiment. So this is the lifted flames, and the flame lifted here. And this is that using microwave to generate singlet or oxygen singlet from microwave discharge. And I measure that ozone generation. I measure that the NOx, and at the same time that the singlet using laser absorption. So this is very easy, and this O2 singlet is a near visible range. So you can really using ICOS cavity, and using this cavity, just similar like a cavity rain down. You can measure this species at near visible range. And you start to see that how much you can generate. So this is that laser absorption curve. And so you can see that I can generate 4,000 ppm about O2 singlet. And then with that a 4,000 ppm, what, this concentration, this is how much the flame lift height is really changed very small. It's only changed a small percent. So they only changed that the flame lift height about 2 to 3% with 4,000 ppm. So in theory, this one is chain branching reaction, Anytime you can perturb chain branching reaction, and you are changing the reaction rate a lot. But in this case, it doesn't. So it is not clear how that the O2 singlet is not affecting that flame speed a lot. And maybe it's because that the O2 singlet is quickly at a high temperature, probably is quickly quenched with interaction with hydrocarbons. I think this reaction rate with hydrocarbons still unknown and in high temperature. In room temperature, and was calculated in high temperature, is not very clear what it is. So if some of them have interest, they might be interested in a reaction rate. So the next thing we'll try to do that how that the atomic oxygen production in a candle flame. So because plasma can generate a lot of atomic oxygen from oxygen, then how much is generated? So this is the diffusion flame, and this is that the nanosecond plasma. You can generate an electrode here and another electrode here. And then this is that the plasma waveform. So you can see from, it's about the 15 nanosecond. The half width about 6 nanosecond with a 6 to 7 kilovolt on peak. So you can really see that how generate the plasma discharge between. You can see how that the flame. So you can see that you can measure using TALIF. You can measure atomic oxygen generation. You can start to see that the extinction limit is enhanced and by both a thermal and also atomic oxygen generation. So this one was like 10 years ago. And so that time is the first time people can measure how atomic oxygen generation in a candle flame with plasma. And this is yesterday I talked a little bit about how ozone can react with ethylene. When the ozone see a ethylene double bond, they form this ozonous reaction rate. So you can see the flame can be either a flashback and propagated back with enhanced flame speed, or a lift off because of that the diffusion things. So with a high oxygen ozone addition, the flame speed is increasing at one flow speed and another higher flow speed with the ozone addition and then the flame. So both of them, they show that the ozone enhances at low temperature reactivity, but only at the high flow rate, you have very high lifted flame height, and then the formaldehyde formed, and in the low temperature oxidation, they diffuse to surrounding environment. That's a weakening that the flame speed. That's why the flame is lifted off, right? So this is that a very interesting things. And again, yesterday we showed that they measured the formaldehyde. You can see a lot of formaldehyde is formed in front of the flame. Here you accelerate the flame. Here that because of a lot of mixing, and and you got the peak fuel concentration decrease in the middle, so that the flame propagation speed is decreased. So the next thing that I want to do, you see what my logic. I understand that the plasma can assist the cool flames, plasma can assist the ignition, and plasma difficult to assist high temperature ignition. So now I try to figure out if plasma can assist ignition, why not to using plasma to accelerate ignition so that ignition is comparable to that the time of combustion in the flames. So the flame speed must be function about ignition times current number. So in combustion book, you don't have any expression or theory about this. How that the ignition times current number affect the flame speed. No one is writing it. But if you have plasma, you can dramatically enhance the ignition delay time, enhance that ignition, and then make it ignition assisted flame. So I see this kind of a lot of, for example, if you have flame stabilizing the cavity, and there's a lot of ignition enhancements going on. The flame speed is not just adiabatic flame speed you measure in the laboratory. Instead, you always couple it with ignition together. So let's do a simple theory. Let's assume this is the reaction rate, and this is my student. So typically that in combustion book, you assume that the reaction in front of the flame is chemically frozen. That means there's no reactivity. But with plasma enhancement or at high temperature with a recirculation zone, you have a lot of radicals come in to the unburned mixture. The temperature is high, the odoignition time is short. So therefore, assume some of the fuel is ignited, partially ignited, and they raise the temperature to TP. And then the rest of the fuel is burned and in a flame regime. Then the question is that how fast this flame can propagate depending on the extent of ignition. So you can, derive, this is the first reaction zone, second reaction zone, and third reaction zone. You can derive an equation that the flame speed with at a high Duncker number will be a function about the flame speed with chemical effusion. That means Duncker number is 0, multiplied by this function. This is that flame temperature minus initial temperature. This is that high temperature ignition temperature minus the temperature, how much that the fuel is partially ignited. If this one is equal, then you have flame speed is infinite. That whatever come, whatever ignite. So, and that you can write that the TP in theory, right one is dependent on Duncker number. Now I have a relationship about flame speed as a function of ignition Duncker number. If you plot this, you can say normalized flame speed is a function of Duncker number. If Duncker number is less than half, you really that not much effect in terms of ignition enhanced. But if the Duncker number is close to above 0.5, you can see the flame speed increase by several times. What does that mean, This means that if you can create an environment, whether it's a plasma-assisted ignition, whether it's a recirculation zone to allow ignition to happen at high temperature, you can dramatically enhance the flame speed by a factor of 2, factor of 4, or even 100. This is exactly what happened in DDT, flame deflagration to detonation. The flame speed initially very slow, but then you form a shock wave that hitting the thing in front of you, and eventually causing autoignition in front of it, and then you quickly accelerate exponentially to supersonic, to detonation speed. So I think this is some simple scaling analysis is really helpful to understand the physics. So let's take a break, and then we'll come back and about what is ignition energy. So I'm speaking pretty slow, but hopefully can finish it.